All right, so today we're going to finish up with error handling and then move on to the next module next week. But we left this off on Wednesday talking about how to do this in C, and I was going to show you an alternative. Again, you can always go ahead and use define and then error type like you used for those magic numbers before, kilometers per hour or whatever we started out with. Or you can use an enumerated type. Now there's not one argument, one strong argument one way or the other. There is a small argument in favor of enumerated types when you go to use a debugger, but we won't get into that until we get into debuggers, so don't worry about it. If you want to use enumerated types or if you want to use a define, it's up to you, unless of course the instructions say to do one or the other, right? The syntax for doing this is an enumeration is a list, so type def enum, and then you can provide the list inside the curly brackets, along with a name for the variable type. The style here is capital underscore casing for the actual values, upper camel casing for the name, day of week in this case. Generally, white space doesn't matter, but it's good to put one value per line so that it's more readable, right? I mean, that's how lists are. If you have a bullet pointed list, right, it's not one bullet and then a comma delimited list. It is bullet, 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 vertical. You generally place this declaration in a header file, a relevant header file for whatever functions actually use this thing. You use the type def enum, comma delimited list, and you name at the end you name it at the end with a semicolon. Generally, again, these are declared in header files. So let's go ahead and take a look at an example here with our math library here, right? So I'm going to go ahead and go over to the math library, and I'm going to declare an enumerated type here for errors, right? So type def enum, and what should I call it if I'm going to make it represent an error, a type of error? Remember, the types of errors that we're looking at here are a negative value for x, a negative value for y, a null pointer, etc., right? So what should I call it? I could call it just error, right? I could call it error code. I could call it error type. All of these are probably acceptable. Let's just go ahead and go with error code, right? Now, you do have to be careful here because you are polluting the namespace. We're polluting the namespace here by naming something error code. If we were to bring in a library that did its own error codes and it called it error code, we'd be sunk, right? So typically what you do is you prepend that with, where are you using this? I'm using this in the math library, so my math error code or something. We're going to keep it simple though, and we're not going to care too much about polluting the namespace, at least for today. What types of errors did we see again? Negative x error, right? A negative y error, right? We might want to distinguish between those two types of errors. And then the final error that we saw is null pointer error. Right, there we go. There's my list. Remember the Oxford comma, you can put that at the end if you want, or just leave it off. But now, there is something wrong with this implementation, right? And it deals with how C actually implements enumerated types under the hood. Be careful. C actually uses integers to represent enumerated types. The list receives an integer value. List items, I should say, receive an integer value, right? Starting at 0. Okay. So, for example, up here with days of the week, what value does Sunday have? If we start at 0, 0, right? What's the value does Monday have? 1. Tuesday is 2, ... Saturday is going to have what value? 6. Why? Because we started at 0, right? Everything in computer science starts at 0. You start counting at 0, right? So Saturday ends up being 6 here. Well, that means that we can use it, but we have to be careful about how we use it. So, for example, we can go ahead and create day of week variable, today, and today is Friday. So I can go ahead and set it equal to Friday. I can create another day of the week, tomorrow, and I can even I can set that equal to Saturday. But what I could have done you can, but be careful with ... If I did tomorrow is equal to today plus 1, right? That will work for Friday going to Saturday, because Friday is 5, plus 1 ends up being 6 Saturday. But what if I did today plus 10? Now, if I treat these as dates, that kind of makes sense, because 10 days from now is October 9th or whatever it is, right? But these aren't dates. These are just enumerated types. So today, Friday, is again, what was it, 5? Right? Plus 10, 15. Do you see a value that probably has a value of 15 in this list? Nope. But C allows you to do this with no warnings whatsoever because of how it actually works under the hood. That this one gets a value of 0, 1, 2. These are just enumerated types. It's syntactic sugar. It is a feature that allows you to do something with human readable words rather than these mysterious magic numbers. But you have to be careful with how you use them, because you can end up doing something like this, right? So don't do that, right? It also doesn't make sense to say day of week when is equal to Friday plus Wednesday. I mean, that's going to be valid, right? Friday is 5. Wednesday would then be what? 3. So 5 plus 3 is 8. But is that a date up? Is that a day of the week up here? Nope. You can go ahead and mod out by it and then wrap around to the beginning of the week. It's not all that useful though. So you do have to be careful. That has negative consequences over here for our error handling. What value does negative x error have? 0. It starts at 0. What value does negative y error have? 1, and then finally 2. But didn't we say that by convention, how do we do our error handling? What's our convention for no error? 0. So if I'm going to do this, I need to make sure that I'm doing it correctly and have a no error value first, so that that ends up getting the value 0. Then negative error, x error is 1, 2, and 3. You can also set these manually. For example, if I say this is equal to 10, then it'll be 10, 11, 12, 13, right? Or you could set this equal to 8, right? Don't get fancy, right? Just leave this, right? There, we're good to go. Now what I can do is I can use these things, right? Over here, instead of returning this mysterious value 20, I'll return negative x error. Instead of returning 42, I'll return null pointer error. And make sure that instead of returning 0, you're returning no error. Right? So you can do something like this. And instead of returning an int, right, then you can return this type that you've created right here, error code. Right? Error code is the type. Again, it's just an alias, basically, for an integer. Right? At the end of the day, when this compiles, all of these things will disappear with actual numbers. Okay. So, questions on that? No? Before we move on, before we move on to Java, I want to, where's the general here? There we go. Yeah, I'll just jump immediately into valgrind here. So I wanted to show you one more tool, one more useful tool here. Oops, I don't want that. There we go. There. Undo that. And we're good. Okay? So now if you stare really hard at this program, you'll probably see that there are some errors. Let's go to lecture general. But sometimes it can be kind of difficult to see errors. So what I'm going to do is I'm going to compile this. It's called valgrind demo. There we go. And I'm going to, by the way, I used the W flag there. That's to hide spoilers. The errors in this program can actually be found using the wall flag, and I don't want you to find them just yet. I want to show you what happens when you've got a really complex program, hundreds of lines of code, dozens of different files. You run your program and oops, you get a segmentation fault. Now, is it at all clear if you, it might be clear with this program what's going on, but is it at all clear if you have thousands of lines of code, dozens of different files, where that happened? Nope. So I'm going to give you a tool now that you can find out when and where that did happen, okay? First of all, let's walk through the program a little bit here. I create two variables, a and x, integer and a double. I set one equal to 42. I set the other equal to 2.5. I make two pointer variables here. Pointer to a successfully points to a. Pointer to x successfully points to x. So in our first two lines here, when we actually print something out, those are valid, right? A is stored at this memory location, x is stored at this memory location, and we successfully see the values that I've assigned to those variables, right? Then I make pointer to x point to 42, and pointer to x, or a to 42, pointer to x equal to 2. Does that sound right? I'll just get rid of that. Right. Now, what am I doing here? I'm making this pointer point to memory location 42, right? I guess that's why I wanted that, right? I'm making x point to memory location 2. Well, there's x right there. X is stored at memory location 2. And this thing, that's hexadecimal. What do you think that's hexadecimal for? Let's look at an online calculator here. Memory location 02A is, memory location 42, right? And so, but I am still printing out the variables by value here. What I do on the next line here is I'm dereferencing a pointer that points to a memory address that doesn't belong to my program. So if you look real hard at here, you'll see that it occurs on line 21. If this is a much more complicated program, you just see the segmentation fault. It died somehow, somewhere, right? You can run a program called valgrind, a.out, which will it's a dynamic analysis tool that will run your program. It'll simulate the running of your program and come out with this report, right? First of all, we see one error from one context here, right? It ended in a segmentation fault, just like we expected, because that's when we ran it by itself. But now let's read this report from the top to the bottom to see if we can find out where it failed. Right? Here is, so we've got these 4 print statements, which were perfectly fine. And then at some point we had an invalid read of size 4. What is of size 4? 4 bytes. How many bytes does an integer take? 4, right? So we had an invalid read of size 4 means that in main somewhere, right, we were trying to read an integer that was invalid. Now, unfortunately, it tells us that this memory address that you were trying to access, the memory address 42, right, that's invalid. It's not part of your program. That's what that report is saying. What line did it occur at? We know that it's at line 21, but valgrind doesn't know what line it's at because I didn't set it up properly. So when you compile a program, all the line numbers, all of the variable names, those get erased because a compiler, an actual machine, doesn't care that you named your variable A, right? It just has some variable that's stored in memory. It doesn't care that you called your function my awesome function, right? It's just some chunk of code in memory somewhere. It also doesn't care that you've got line 12 and 13, and then you had a blank line, and then line 15 and 16. All those lines get erased when it gets assembled into assembly code. Right? Assembly code, we saw that in the first week, right? It's this other, I think I can, what's the flag for doing it? Does anybody remember? Is it S? GCC S? Valgrind demo? Nope. All right. I forget the flag to just show me the assembly. But remember, I showed it to you, and then we did a hex dump, and we saw what it looked like. It was a completely different language. This C code gets translated, assembled into assembly language. Right? A completely different language. The line numbers over here have nothing to do with the line numbers over here. So what I need to do is I need to tell GCC, preserve all of those line numbers, preserve all of that metadata, preserve all of the variable names and the function names, etc., so that I can debug and run this through analysis tools. Right? The G flag does that for me, right? And valgrind demo. G, it's short for, I believe, the GNU debugger, which is something that we'll look at later on. But if you give it the G flag, then all of the line numbers will be preserved. Right? Let me run valgrind again. Valgrind a.out. Now we'll get the same report here, but we'll get more information. Right? There. Before it didn't know what line number it was occurring on. Now what line number does it occur on that we know of? 21. We can immediately jump to that line and say, okay, what's going on here? Right? We get a hint that there was an invalid read of size 4. Oh, it's probably this thing right here. Right? If I took that out, we would still get an error, GCC. Right? If I ran this again, I'd still get a segmentation fault, but now it's going to be on line 22. Right? GCC, and let's run valgrind again. And this time, okay, good. Predict what the message will be. If I'm trying to dereference a double pointer and it's invalid, is it going to be an invalid read of size 4? Nope. How many bytes does a double take? Hint, it's in the name. 8. And we can come up here and see that on line 22, indeed, we had an invalid read of size 8. So a very, very useful tool here. We'll come back to it later on after we've done dynamic memory. It can actually detect memory leaks and stuff like that. So just as a quick review here, again, valgrind. It is a tool demo. Right? Valgrind. Recall that the WALL flag can be used as a linter, a static analysis tool that examines code before you compile, right? Static refers to the code, it's static, right? It's just fixed, that's what it is, that's the code. So when it analyzes that code, it's analyzing it statically. Once it's been compiled and it runs, that's called a dynamic analysis tool. You can also use dynamic analysis tools. Tools that examine a running program after compilation. There we go. Example, valgrind. Usage, 1. First of all, be sure to compile with the G flag to preserve line numbers and variable names, etc. Otherwise, it's not going to be able to tell you, well, it occurred at this memory location, right? But it's not going to be able to map that back to your original code on line 21 or line 22 or whatever, right? So be sure to compile with that. Then you can run it using valgrind a.out, which produces a report, telling you what lines it failed on, but not necessarily how. It's not going to say, well, on line 21, you dereferenced a null pointer. That null pointer, of course, you can't do that. You probably wanted this code instead, right? It's not going to be that sophisticated. It's just going to tell you, this is what went wrong, right? Here's the memory. It's up to you to do your own investigations. Now, remember that I was suppressing all the warnings. If I turn on all the warnings on valgrind demo.c here, you'll see immediately that the static analysis tool was able to detect, wait a second, you're doing some really bad stuff here. You're setting pointers to literal values. You are setting pointers to integer pointers to point to double values and vice versa, right? So your first line of defense is a static analysis tool, the WALL flag. Your second line of defense is once you've got a segmentation fault, fire up valgrind and at least find the line number that it happened on. Okay? Don't rely on print statements. They are not going to be the best debugging tools. We'll look at a proper debugger later on. Right? Okay, so let's take a look at Java. So Java is completely different. Java uses what are called exceptions, exceptions handling instead of defensive programming. An exception, right? Well, it's kind of like in real life. It's an exception to the rule, is an interruption of the normal linear control flow of a program. Interruption. Okay, I can't spell it. 2 R's. There we go. So the philosophy is completely different here from defensive programming. The philosophy is, instead of looking before you leap, it's go ahead and leap before you look. Because try potentially dangerous code. If it ends up with an exception, if it ends up with an error, we'll catch you as you fall off that cliff. Go ahead and leap, right, before you look, because we'll catch you. Right? And the try and the catch here, those are key words that are used in Java. That's why I'm using that analogy. If you fall, and then we'll put you back up on the top of the cliff because you fell. We caught you, and we'll put you back up there, and then we'll let you decide what to do. Right? Do you quit out of the program? Do you ask for a different input? What are you going to do? Right? There are lots of advantages with this. First of all, it's a more modern way of doing it. But with error codes, there's no semantic meaning to the code. I'm just returning a number, right? Even if I end up using, what were we using there? An enumerated type. Where is that? Nope, that's not it. My math. Right. Even if I use an enumerated type, these are only human readable words, right? At the end of the day, they're still just numbers, right? And you can get them wrong, right? You can go ahead and add 10 to today, right? And be out of range of all these numbers. But with exceptions, you have semantic meaning. One type of exception is not the same type as another exception, and you can tell the difference at compile time before the program is actually running, right? With error codes, it's just a number. Even if you don't use magic numbers, they're still just integers at the end of the day. With exceptions, it does have semantic meaning. You've probably seen some of these exceptions before, right? Null pointer exception, arithmetic exception, input mismatch exception, right? These are 3 distinct different types of exceptions that can all be distinguished by the language itself. The language itself it can distinguish between a number, but it has no semantic meaning that it maps it back to a certain type of exception. These do, right? These have a strong association with the type of exception. Another advantage is that defensive programming often leads to this large, nested, separate if-else-if conditions, right? And go to fail error kinds of things. I mean, we saw that with this very simple example. What did I have to do for error checking? If it's this type of error, else if it's this type of error, else if, else if, else if, else if, right? If you've got 10, 20, 30 different types of errors that can occur, right? You've got this huge chunk of code and everything, right? Whereas with an exception handling system, you don't necessarily have to have that. I mean, if you want to handle all 20 of those situations completely differently, you'll end up with 20 lines, 20 blocks of code, right? Because you do need the code to handle all of those differently. But some of them you don't care about. A null pointer exception, if something's null, that should be the end of the program. I don't want to write code to have to handle that, because that should be fatal, right? I don't want to handle that. Arithmetic exception, if somebody divides by 0, that's on them, right? I'm not gonna handle that. I'll just let the program die, and then it's their fault. They need to go and fix the program, right? So the way that Java works, let me go over to Java here, right? Is that you can try some dangerous code. For example, let's go ahead and create a string here. S is equal to hello. What I'm going to do is I'm going to try to marshal that. I'm going to try to parse that out as a number, right? So integer I is equal to, or let's say x is equal to integer dot parse int s. There we go. There. Oops. End of main. There we go. So is this going to work? Is that an integer? Nope. What's going to happen if I run this? A number format exception, right? For input string hello, right? That's what it's throwing this type of exception here, right? So what I could do instead is I could surround that with a try catch. Try this potentially dangerous code where it could result in a number format exception, right? And catch it if that occurs. Catch a number format exception. And you need to give it a name. Generally, they're just NFE because, well, what is it? It's an exception. But if we're gonna catch multiple exceptions, you can go E1, E2, E3, or you can go ahead and use the convention of using the first letter of the exception's name, NFE in this case. And then I can choose to handle this situation somehow, right? ... right? Maybe I'll just log an error message here and quit, right? That's possible. Or maybe I'll just go on, right? System.out.println, done. Right. There we go. I do need to fix that. There we go. All right. So now this is going to be a little bit different, right? What am I doing in the event of a number format exception? Nothing, right? I'm choosing to move on with the rest of my life and the rest of this program. What will happen here? It'll just print done, right? Okay, great. So if it is actually a valid value, right, then we'll get a number for x, and we'll print system.out.println x is equal to x. There we go. So if it's valid, 1, 2, 3, and then done. If it's invalid, hello, then we choose not to, we still try to parse it out, but we end up catching this number format exception, and then we'll, we choose to handle that some way, right? All right, well, I want to compute the inverse of that. Y is equal to 1 divided by x, right? Now remember that this needs to be a double. One of these at least needs to be a double, right? Double y is equal to null, and then we'll go ahead and say y is equal to this thing, right? And then we'll print that out as well. X, y, and y. So 10. What's this going to end up printing? There's no exception here because it successfully parses it as an integer. Then we compute the inverse of it, the reciprocal, and print out x and print out y. So it's going to print 1 and 10, excuse me, and then 0.1, and then done, right? What if instead I gave it this value? What's going to occur now? Is this going to be a number format exception? No, 0 is a number, right? Okay, fine. We're good here. 1 divided by 0, though. What's going to happen? Let's find out. Oh, infinity, right? So this should have been an arithmetic exception, right? I thought 1 divided by 0 would end up being an arithmetic exception. Java, what throws arithmetic exception? Maybe we'll have to throw it. Come on. Huh. Okay. I thought it would, maybe if I do this as an int, and that, try this. Does it only work with primitives? Oh, wow. Who would have known that I learned something today? It only throws an arithmetic exception if it ends up being 0. I imagine that it ended up being null or something, right? Anyway, we'll go ahead and leave it like this. It now throws an arithmetic exception, which I can also catch. Arithmetic exception. AE. Right? And choose to handle in a different way somehow. ... But in either case, did it print done? Nope. Before I handled this, it was treating that as a completely fatal thing. The entire program ended. If I choose to handle this in some other way, say just printing a message, system.out.println, you cannot divide by 0, setting a default value, ... And maybe we'll go ahead and reset x equal to 1 and y equal to 2 or something, right? Y has to be outside. There we go. And now we're good, right? And then I can print those out down here as well, or maybe just instead of. I'll leave it like this for now. Come on, what's wrong? Fine. Null and 0. It was complaining down here because I didn't have an initialized value, right? So now let's run this. This will be a divide by 0 error, so this will end up being an arithmetic exception. So what happens when I try to divide by 0 at line 16 is an arithmetic exception is thrown, it's caught on line 22, and then proceeds to execute this code down here, which prints this error message and then sets default values of 1 and 2. So that down below, the second time that we print them, it'll be 1 and 2. Note here, however, we did not print these two up here. Why not? The exception was thrown on line 16. Right? It immediately jumps. It's an interruption of the normal control flow, right? A, B, C, D, E, right? If you've got these statements, right? It's an interruption at line 16 that jumps down to line 22, right? You could also do, say, a null pointer exception. Catch a null pointer exception, NPE, right? And then choose to handle it a different way, a third way, ... Right? So by being very, very specific as to what type of exception you're catching, right, then you can choose to handle it in different ways. What if another exception occurs that I didn't anticipate, just a generic exception? You can do that as well, exception E. Right? And then what you generally do here is e.print stack trace. Right? That will end up printing what happened and where with a full stack trace on line numbers and stuff like that. And then what I'm going to do is we can system.exit. We could do that rudely on them if you wanted to. Otherwise, what I'm going to do is I'm going to do a catch and release. So I'm going to throw a new runtime exception, E. Right? What I've done is I've caught this exception. Anybody go fishing? Any anglers out there? No? Okay, well, usually like up at the lake, we've never caught anything with my kids, but up at Flanagan Lake in Omaha, we go there, we try to, it's a catch and release lake. You're not allowed to take the fish home and eat them. You wouldn't want to eat them, believe me. But anyway, you catch and release, right? That's usually what you do with fish, unless you're actually wanting to eat them, and then you need a license for that or something. But in any case, what we're going to do is catch and release. I caught this exception, but it's a generic exception that I don't know what to do with it. So what I'm going to do is I'm going to wrap it up in a runtime exception and rethrow it. That ends up being a fatal exception, and it kills the entire program. Right? So let's go ahead and run this again. We get the same results here. How can I force a different type of exception? I know. I'll try to open up a file. Scanner s is equal to new scanner. We'll look at file ILO later on. New file. Foo. There we go. Import all this stuff. Import. Import. All right, fine. Okay. Oh, is it? Thank you. There we go. Now I can import a file. There we go. And I'm missing a... There we go. All right, and S. Oh, I've already used S, so I'll use SC. All right. There we go. I'm going to try to open up a file named foo that doesn't exist. Save this, and now it compiles. And it should throw like a file not found exception. It should. Come on. All right. Do something with it. sc.next int. Unless I do actually have a file named foo. Oh, come on. Oh, I know what I'm doing. I need to shut off the other error here so I can actually get to that line of code. So 1, 2, 3 here. Now 1, 2, 3, it'll parse it correctly, it'll divide by it correctly, it will print, and then it'll try to open up this non-existent file here. Right? There we go. File not found exception, foo. But you see my full stack trace here, right? That what I did is I caught this file not found exception, I wrapped it up in a runtime exception. There we go. There it is, right? This runtime exception right here, right? So that's why we're getting two copies of this stack trace, because I caught it, I wrapped it up into another exception, and then I rethrew it because I didn't want to deal with that. How can you possibly recover from an input file that you expect to read if it doesn't exist, right? We're simply going to rethrow it, right? And say, I don't know how to deal with that. So I rethrow it as a runtime exception and let it kill the entire program with this stack trace as a result. So all together here. Yep. Okay, I guess I'll do this then. So in Java, all exceptions are a subclass of throwable. Note that I threw an exception. You can make your own types of exceptions if you want to, and then throw them, right? And there are these subclasses of throwable. All exceptions, all error types are throwable. You can throw them in the language, right? That way you can try, it gets thrown, and then you catch it, right? An error is one type of exception that you never, or one type of throwable, I should say, that you never really deal with. It's, that indicates that something happened with the Java virtual machine. The Java virtual machine could run out of memory. It could encounter illegal or invalid Java bytecode. There's no way that you're recovering from that. If the entire machine dies, your code that is operating on top of the machine dies with it, right? So there's nearly nothing that you can do with those. But an exception is what you can deal with in your code, right? There are two types of exceptions here. There's just a general checked exception, what's called a checked exception. There we go. Where you're forced to surround it with a try and catch, right? And if you don't do that, then the compiler won't let you compile. What's one example? Exception. I don't think file not found exception is a throwable. I think it might be. Let's go back to our code over here. This was working before without too much incident because I had already surrounded this with a try catch. Let me do it up here before I do anything else. I'll try to open up this other file over here named bar. And I'll call it SC2. Why won't it let me compile? Let's hover over it and find out. Unhandled exception type, file not found. Right? This was something that was introduced into Java a long time ago, and it was thought that it was a good idea at the time. Right? It turned out that it was not a good idea at the time. It was a terrible idea. It was never adopted by any other language except for C++, and even then it's still optional. These are called checked exceptions. An exception that you must surround with a try-catch. So the way of dealing with this is to surround it with a try-catch, catch that exception, and then do what with it? Exactly what we were doing down here. You throw it as a new runtime exception. You catch and release. E1. Right? Because there's not much you can do about it, right? The philosophy that they were thinking of at the time was that a checked exception is something that you should be able to recover from. But all of the checked exceptions that they actually put into Java, like this, are not exceptions that you can reasonably recover from. If you want to read from a file named bar, and it doesn't exist, how can you recover from that? If you're trying to connect to a remote database and you don't have the correct password, right? How can your program recover from that without human intervention, right? So it was an ill-conceived idea at the time, and they realized that, and they kind of backed away from it. It's not really used all that much anymore, but we're still living with that legacy here that some of the older stuff in Java has checked exceptions that end up throwing this stuff. The solution is, unfortunately, just to surround them with try catches. The real solution would be to take these out of the language, which makes it non-backwards compatible. It would break all future code running on older machines. So you have to weigh the choice of getting rid of something that turned out to be a bad idea or making sure that everything still runs. You choose that make sure that everything still runs. And we're still living with that mistake now 20 years later. Right? But most of them are unchecked exceptions. For example, runtime exceptions. Right? A runtime exception is an unchecked exception where you don't have to surround it with a try catch. You can if you want, and if you want to handle that situation with your error handling, fine. But you don't have to. It will still compile, it will still run. If you don't catch a runtime exception, then it just keeps bubbling up the stack trace until finally it results in either it's caught or it results in killing the program. Right? Examples of those would be, of course, the ones that we were using here. Number format exception, arithmetic exception, null pointer exception, but general exception, that's a catch-all term. That's just a generic term here. Right? Unfortunately, we have checked exceptions still in Java. It's a wart. It's one of the bad things about Java. Right. All right, so questions so far on any of this? No? There's also a try with resources that we'll look at later on. There's you can say, well, I want to deal with number format exceptions and arithmetic exceptions the same way. So you can use this syntax. What is that thing right there? It looks kind of like an or, right? If we get a number format exception or an arithmetic exception, we can go ahead and treat that all the same way, right? But it's only one Sheffer stroke. It's only one vertical pipe, right? There's some other things that dealing with error handling here, but that's as deep as I want to go for this. Right? You can do defensive programming. For example, int a and b, a is equal to 10, b is equal to 0. Right? And you can go int x is equal to, or did I already use b? Oops. Nope. X is equal to a divided by b. Right? The compiler is not going to complain about that, but I can say, surround that with a try. Right? If I'm about to divide by 0, right, I can go ahead and, actually, sorry, and what I wanted to show was, if b is 0. I can do a little bit of defensive programming here. 0. Then I will do throw new runtime exception. You cannot do that. ... There we go. Else, yeah, you can go ahead and do that. There we go. Go ahead and divide by b. Right? You can throw your own exceptions if you really want to. Generally, what I'm going to say is just throw a runtime exception. You can make your own exceptions if you really want to. I think maybe in the hack it shows you how to do that, but I won't bother showing it here. Right? It's pretty easy. You just have to create a class. But there. What would our do I have my math here? There we go. What would it look like here? So I'm not going to return a return code here with arithmetic geometric mean. Instead, I'm simply going to check if it's negative, right? If x is less than 0 or y is less than 0, then I will throw a new runtime exception with the message that arithmetic geometric mean is only defined for positive values. There we go. Now in my math tests, right? Nope, that's that's JUnit there. My demo over here. Right? I'll go ahead and try my math.agm of -10 and -20. There we go. And capture that result. Double result is equal to that. Now what's going to happen here? If we jump into that function, we check to see that they're negative. If that happens, we throw this runtime exception. But are we bothering to catch that? Nope. So what ends up happening is it's going to be a fatal exception. Your choice of not catching that has consequences for your program, right? It's just going to die with that message. Again, you can surround that with a try catch. It was a exception, a runtime exception. I'll just catch all exceptions here, and then do something about it. ... Right? Reprompt for input, do whatever. Again, 99.9% of the time, if an exception occurs, you probably want it to be fatal, right, for all of your programs. Now that story changes if you're in a like say a server environment where you've got multiple users. If one user enters bad data, right, and results in they enter a bad date, February 30th, for their birth date, right? It results in an exception. Do you want the entire server program to die for all the other users that are entering good input? No. Instead there, what you do is simply just log it, and then let it continue, right? Log an error message, maybe then go back to the user and say, that's not a valid date. We're gonna exit you out of the program and let all the other good users use the program, right? So there are instances in which you want to say, log the error message to find out what happened and when and why, and let it be fatal, but let it be fatal for one person instead of the entire population of people that are using your server. Right. All right. Any questions on error handling? No? I'm just going to go ahead and copy this entire chunk if you want it in the notes. All right, there we go. All right. We've already talked about unit testing. So the next thing would be arrays or collections, which will start next week, of course. Kind of a little bit ahead, but that's because we had that off week, which is new this year, at least in these courses. Any questions? No? All right. Well, then I believe you might be getting an email soon about a midterm evaluation for this course. I opted in on all of my courses to get a midterm evaluation. This would be your first time probably filling out a course evaluation. It is completely anonymous. You can feel free to opt out if you want to, but when you go into Canvas, you'll see a message at some point that says, please fill out the midterm course evaluation. I take those just as seriously as I take the end of term evaluations as well, which means I take them very seriously. So if you can, go ahead and fill those out. Let me know how the course has been going so far. Particularly, I'm interested in the pace. Since this is an honors course, we try to go a little bit faster. It seems to, at least personally, I don't want to bias you. So I'm not going to tell you what my take is on it, because I don't want you just parroting my take. I want to hear your take on it. So go ahead and make sure that you're filling that out. I think that you'll get it on the 2nd. So they told me that it opens on the 2nd. Has anybody already gotten the email on it? Okay, all right. Eventually, when you log into Canvas, it should bother you until you do it or until you say that I'm not going to do it, and then it'll go away. So either way, please go ahead and take those seriously and fill those out. Again, it's completely anonymous. I won't even know who filled it out and who didn't fill it out.